Okay, so in this problem we have a bar, which is attached with a thin spring, and we're told that the bar has a weight of W and that the spring is unstretched when theta is equal to 0. And given that information, we're asked to determine the angular speed of the bar at theta is equal to 0 if the bar just reaches theta is equal to 90 degrees before coming to rest. So what I can do is I can define two states here, state 1 where the bar is upright, and state 2 where the bar is going to be oriented something like this. And let me just kind of sketch in here what that's going to look like. And basically what I'm going to do is, since I'm looking for an angular speed after change in position, I know I want to use the work energy equation. Now since I want to use the work energy equation, it makes sense to draw a free body diagram of this system. And if I do so, you'll note we'll have two reactions at the bottom of the bar, which I can call OX and OY. We'll have the weight of the bar, which is going to act at the center W, and we'll have some force of the spring, which I'll simply call FSP. Now if we look at these, we know OX and OY are not going to contribute any non-conservative work because point O doesn't move. W is going to be accounted for in the potential energy, as is the force of the spring. And so I can write down the work energy equation, namely T1 plus V1 plus U1 to 2 non-conservative is equal to T2 plus V2. And I can note right away that the non-conservative work in the system, U1 to 2 non-conservative, is going to be 0. I can also note that the object just reaches 90 degrees before coming to rest, which means that T2 here is going to be 0 as well. So now I can work out and find each of the rest of the terms in this equation. If we start with T1, we can note that if we express the kinetic energy about point O, then we'll have an object in pure rotation. So I can write this as 1/2 I about O times omega 1 quantity squared. I about O can be rewritten using the parallel axis theorem as 1/2 times I about G plus m times the distance between O and G, which I'll write as dOg quantity squared, times omega 1 squared. I can then note that I for a bar about its center of mass is 1/12 mL squared, and the mass from O to G is going to be L over 2 quantity squared, and I'll have that times omega 1 squared. If we work this out, we'll get T1 is equal to 1/6 times mL squared times omega 1 squared. V1, the initial potential energy, will be a function of where I choose my datum. Let's go ahead and put our datum down here at the bottom. If I do that, the initial spring potential is going to be 0, and the initial gravitational potential is going to be m times g times, in this case, L over 2, because we know the center of mass of the bar, since it's homogeneous, will be located distance L over 2 above the datum when theta is equal to theta 1, which is 0. At the second state, V2 will have some potential energy contribution. The gravitational potential, since the bar is on the datum, will be 0, but we will have a contribution due to the spring stiffness, so in this case we'll have 1/2 K times delta squared. Delta, of course, will indicate the amount of stretch in the spring, and so to do this, we'll note that the spring at state 2 has a length given by the square root of the 6 feet quantity squared plus L squared. And that's, of course, the hypotenuse of the triangle that exists from the point of top attachment to the spring to the state where the bar is on its side. And then I'll subtract off from that the unstretched length, which will be the difference of 6 minus L. If we plug in the fact that L is equal to 4 here, we can get a nice numerical quantity. For delta, square that, multiply it by K and 1/2, and we can get a nice numerical result. If we go ahead and take these three expressions, substitute them back into the work energy equation, noting that the two terms already in there are equal to 0, we can take this equation and solve for omega 1, the initial angular speed, which is exactly what you're asked to do in this problem. From there on out, it's a straightforward numerical exercise, and one I know you have well under control. So I'll simply bid you adieu, and the best of luck. Take care, everyone.